Welcome to the deep dive. Today we have a very focused mission. We're taking a really dense chapter from the A-level chemistry course book, chapter 26.
Carboxylic acids and their derivatives.
Exactly. And we're going to break down, well, every core concept, every definition, mechanism, all of it in sequence.
That's right. This chapter is a real pivot point. You move from the kind of foundational reactivity of carboxylic acids to these highly reactive intermediates.
Wait, acyl chlorides.
Acyl chlorides, yeah. We'll synthesize the key takeaways on, acid strength, some unique oxidation processes, and the mechanism that explains why some of these compounds hydrolyze so fast while others won't touch water.
Our listener wants a clear, structured summary to get up to speed quickly. So let's start with the context. Those long-chain carboxylic acids we call fatty acids.
Good place to start.
Yeah.
So when you hydrolyze fats or oils, you get these long-chain carboxylic acids. We call them fatty acids.
Now, they have some distinct features, right?
They do. They typically have unbranched chains and an even number of carbon atoms, like octadecanoic acid, which is CH3, then 16 CH2s, and then the COH group.
But what's really fascinating is how the double bonds change everything.
Oh, absolutely. This is where the classification comes in. We call them monounsaturated if there's one carbon-carbon double bond.
And polyunsaturated if there's more than one.
Exactly. And every single one of those double bonds introduces the possibility of cis-trans isomerism.
So let's try to paint a picture of that. If we take octadec-9-enoic acid, what's the difference?
Okay, so the trans isomer, its chain is, well, it's pretty much straight. But the cis isomer, that double bond, creates a really noticeable bend or a kink in the chain.
And that one small structural difference has huge consequences for their properties.
It really does. The straighter trans fatty acids, they can pack together much better, much more tightly.
Which means they have higher melting points.
They have higher melting points. You need more energy to pull them apart.
And this is where it connects directly to the real world, to the health discussions. Trans fatty acids are linked with health risks.
Right. They're often produced when plant oils are partially hydrogenated.
To make margarines and things like that.
Exactly, to make them shreddable. This process saturates some bonds, but it also converts some of the natural healthy cis isomers into the trans isomers, which raises the melting point.
And the big picture impact, why is that a problem?
Well, consuming trans fats disturbs the balance between low-density lipoprotein, that's the LDLs or bad cholesterol, and the high-density lipoproteins, the HDLs or good cholesterol.
Which can lead to circulatory problems down the line.
That's the connection.
Okay, let's move into the first main section, 26.1, the acidity of carboxylic acids.
Right, so the definition we start with is that carboxylic acids are weak acids.
Meaning the dissociation equilibrium lies far to the left.
Far to the left. It favors the undissociated molecule. We measure this with the dissociation constant, Ka. For something like ethanoic acid, Ka is tiny. It's about 1.7 times 10 to the minus 5.
That exponent -5 tells you almost nothing is dissociating.
Very little. And the smaller the Ka, the weaker the acid. But, and this is the important part, even though they're weak, they are still much stronger acids than alcohols.
Okay, so why is that? There must be a structural reason.
There are two main reasons, and they work together. First, the OH bond in the carboxylic acid is inherently weakened by the carbonyl group, the C double bond O that's right next to it.
It's pulling electron density away.
It's pulling it away. But the second reason is the most important one. It's all about the stability of the ion that's formed after the proton leaves.
The carboxylate ion, the minus COO-.
That's it. And that ion is stabilized by the delocalization of electrons.
So the negative charge isn't just sitting on one of the oxygen atoms?
No, it's spread out. It's shared across both oxygen atoms and the carbon. This delocalization spreads out the negative charge, reduces its density, and makes the ion much less likely to just grab an H+ back.
A more stable ion means a stronger acid?
A more stable anion, a stronger acid. That's the rule. And this gives us a sort of strength hierarchy.
Right. Carboxylic acids are stronger than phenols.
Which are, in turn, stronger than alcohols.
Yeah. Now, what happens when we start attaching other groups to the molecule? Substituents.
This is where it gets really interesting. If you add electron-withdrawing groups, like chlorine atoms, right next to the COH group, you make the acid stronger.
So pulling more electrons away makes it even more acidic. Why?
It's that same principle, just amplified. The chlorine pulls even more electron density away, which weakens the OH bond even further. And crucially, it helps to spread out and stabilize the negative charge on the carboxylate ion even more.
So you can see this really clearly if you compare ethanoic acid to, say, trichloroethanoic acid.
Oh, it's a huge difference. With 3 strongly electron-negative chlorine atoms all pulling electrons away, the effect is massive. It's a much, much stronger acid.
So the rule is,
Yep.
the more electron-withdrawing groups, the stronger the acid.
That's it. And conversely, electron-donating groups, like the methyl group in ethanoic acid, do the opposite. They push electrons in, which strengthens the OH bond and concentrates the negative charge on the ion,
Making it a weaker acid?
making it less stable and therefore a weaker acid.
Okay, that covers acidity. Let's shift gears to section 26.2, oxidation. Now, usually, carboxylic acids resist more oxidation.
Yeah, that's the general rule. Once you've made one from a primary alcohol, for example, it's usually done. But there are 2 really common exceptions that are actually strong reducing agents.
And the first one is methanoic acid, HCOH.
Right. If you look at its structure, it's kind of unique. It has the aldehyde functional group sort of hidden inside the carboxylic acid structure.
Which means it can be oxidized further?
It can.
Hmm.
It can be oxidized to carbon dioxide and water, even by mild oxidizers like Fehling's or Toland's reagents.
The ones you use to test for aldehydes. So with Toland's, you'd get the silver mirror.
You get the silver mirror.
Yeah.
And with Fehling's, you get that red copper eye oxide precipitate.
Okay, and the second exception?
The second is ethanidioic acid, a dicarboxylic acid, HOCCOHR.
And this one needs a stronger oxidizing agent.
It does, something like acidified potassium manganate. And this reaction is actually really important in titrations.
Right, for standardizing the potassium manganate solution, the stoichiometry is 2 moles of manganate to 5 moles of the acid.
It is, but there's a really cool detail here called autocatalysis.
Okay, what's that?
The manganese 2 ions, the Mn2 plus H, which are formed as a product of the reaction, they actually act as a catalyst for the reaction itself.
Wait, so the reaction produces its own catalyst?
It does. So it starts off slow,
Yeah.
but as more and more Mn2 plus is formed, the reaction speeds up. You can actually see it accelerate as the titration goes on.
That is fascinating. Okay, now for the big pivot. Section 26.3, acyl chlorides.
Right. These are, as you said, chemical powerhouses. You take a carboxylic acid, you swap the Evis OH group for a chlorine atom, and you get RCOCl.
And they're so important because they're just so much more reactive than the carboxylic acids they come from.
Dramatically more reactive, which makes them fantastic synthetic intermediates.
So how do we make them?
You start with the carboxylic acid, and you can react it with one of 3 reagents. There's solid phosphorus V chloride, PCl5, or liquid phosphorus 3 chloride, PCl3.
But there's a third one that's usually preferred, right?
There it is, liquid sulfur dichloride oxide or thionyl chloride, SOCl2. And the reason it's preferred is purely practical.
What's the advantage?
The other 2 products it makes, sulfur dioxide and hydrogen chloride, are both gases. So they just bubble out of the reaction mixture.
Leaving you with a much purer product.
Exactly. It leaves the acyl chloride as the only liquid, which makes the purification way, way easier.
So let's get to the core question. Why are they so incredibly reactive? What is it about swapping an OH for a Cl that changes everything?
It all comes down to electron withdrawal, but on an extreme level. The carbonyl carbon, the C and the C double bond O, is already electron poor because the oxygen is pulling electrons away.
Yep.
But now you add a second, very electronegative atom, the chlorine, also pulling electrons away from that same carbon.
So it's getting pulled from 2 directions.
2 directions. And this dual pull creates a very large partial positive charge, a big delta plus, on that carbonyl carbon.
It's basically putting a giant attack here sign on that carbon.
That's a perfect way to put it. It makes it extremely susceptible to attack from nucleophiles, any molecule with a lone pair of electrons ready to donate.
So what does that reaction look like in general terms?
Well, the general mechanism for all these reactions is called an addition-elimination reaction. The nucleophile first adds across the C double bond O.
Creating a temporary intermediate.
Right. And that's immediately followed by the elimination of a small molecule, which is almost always hydrogen chloride gas.
And that's what you see as those steamy white fumes.
That's the steamy white fume.
Let's look at some specific examples. What about hydrolysis with water?
This is the most dramatic one. Acyl chlorides react with water instantly, vigorously, even with just cold neutral water.
And they just turn back into the carboxylic acid.
They turn right back. It's a very rapid reaction.
And it's worth contrasting that with other chlorine compounds, isn't it?
Oh, absolutely. Think
Yeah.
about a chloralkane. To get that to hydrolyze, you need to reflux it with strong alkali.
And an aryl chloride, like chlorobenzene.
Forget it. It won't hydrolyze at all under normal conditions. It's completely unreactive.
So the order of reactivity is just staggering. Acyl chloride is off the charts, then chloroalkane, then aryl chloride is basically inert.
It is. And that inertness of the aryl chloride is because the chlorine's lone pair of electrons overlaps with the delocalized pi system of the benzene ring.
Giving the CCl bond some double bond character.
Exactly. It makes the bond much stronger and much harder to break.
Okay, what about reacting acyl chlorides with alcohols or phenols?
That's how you make esters. And it's a much better way to do it than using a carboxylic acid.
Why is it better?
2 reasons. It's faster, and crucially, the reaction goes to completion. It's not a reversible equilibrium. You get a much higher yield of your ester.
So it's a more efficient synthesis.
Much more efficient. And finally, you have the reactions with ammonia and amines.
Which form amides?
They form amides, yeah.
Ugh.
Ammonia gives you a simple amide. A primary or secondary amine will give you a substituted amide.
And here's a good lab observation. You tend to see fewer of those steamy HCl fumes in these reactions. Why is that?
Because ammonia and amines are bases. So as soon as the hydrogen chloride gas is produced, it immediately reacts with any unreacted ammonia or amine in the flask.
And it forms a salt.
It forms a white ammonium salt like ammonium chloride, so it basically traps the HCl before it can escape as gas.
So let's bring it all together for you, the learner. We've covered the key drivers in this chapter.
We have. It's the role of electron density in acid strength, that delocalization.
The unique reducing power of methanoic and ethanidioic acids.
And the synthesis, and of course the hyperreactivity of acyl chlorides.
The primary takeaway seems to be that reactivity in these organic compounds hinges really entirely on the structure of that functional group.
That's the whole story. Whether it's electron delocalization, stabilizing an ion, or 2 electronegative atoms creating a highly positive center, it's the structure that dictates the reaction pathways every single time.
All right, for a final provocative thought for you to mull over, we saw how adding just one chlorine atom significantly increases the acidity of ethanoic acid. Now, how would the acidity of an acid with a bromoine atom compare to that of chloroethanoic acid, given the differences in their electronegativity?
Something to think about. Keep exploring those mechanisms, and thank you for joining us for this deep dive.